Thanks for tuning in. My name is Erica Whitney,
And my name is Skylar Elmstrom.
and we are both research assistants at the Institute for Environmental Toxicology and Chemistry within Western Washington University's Huxley College of the Environment. Why talk about data management? Well, according to a 2016 study asking data analysts what they spend the most time on, 60% reported that it was cleaning and organizing the data. Although perhaps less than exciting, data management is the foundation of the work that we do as researchers.
Today we will provide a project introduction to give context for the type of data and analyses we are doing, an overview of our data management goals, QA/QC recommendations and anecdotes, including some of our mistakes and discoveries while approaching data wrangling challenges. And finally, we have a few recommendations for researchers to consider when structuring their data.
Our project is an environmental risk analysis for the Upper San Francisco estuary, considering the impacts of stressors such as water quality parameters and chemical contaminants to endpoints selected by stakeholders, including Chinook salmon, striped bass, and macroinvertebrates. We use Bayesian network relative risk modeling to evaluate the relative risk posed by these stressors to those endpoints for each region of the study. In the interest of time, let's just say it is a probabilistic model which can offer flexibility in the types of data utilized. To parameterize the stressors in our model, we use massive and complex datasets.
To facilitate collaboration and assimilation of new participants into a complex project, clear organization of data and analyses is essential. We created a data management plan with three primary goals: maintain an organized product, maintain reproducibility, and document every step. Keeping our project organized helps us maintain a deliverable product from start to finish for sharing with stakeholders, getting help, and publishing. To keep our project reproducible, we adopted a GitHub workflow in RStudio to share code, collaborate, revise, and document every step of our data processing. We worked together to create markdown documents for our project R code so that every team member could reproduce results, troubleshoot, or join or take on a task more efficiently. Complex GIS tasks were documented using ArcGIS Model Builder and typed documents.
For the water quality stressors in our model, two huge databases we used are SEDEN, managed by the California State Water Board, and SURF, managed by the Department of Pesticide Regulation. These contain standardized information from many projects and agencies, offering over 300,000 records within our study area and timeframe. Locations of those points are on the map. To optimize the temporal and spatial coverage in our model, we chose to integrate these databases. Because each was designed with a different goal in mind, integration required overcoming differences in content, organization of data, and detection of duplicated data.
Our data processing strategy can be broken down into a cycle of 4 tasks: metadata, exploration, QA/QC, and integration. Metadata is our first stop when acquiring a new dataset. As users, we ask, how is the data structured? Who do I contact with questions? And how is the data intended to be used? The metadata is where we expect to answer a lot of our questions about how we should use the data. Exploring gigabytes of data on student laptops or remote connections to campus was not ideal. We began using R and R Markdown for all data processing rather than typical spreadsheet editors for the sake of reproducibility, efficiency, and for error detection tools. We used API requests or spatial and temporal queries in R to narrow our datasets. Our initial exploration focused on data quality. We established criteria for data quality to meet our project needs. Is the location data correct and is the coordinate system defined? Are the units of a result specified? Are the results numeric? What do blank results mean? Additionally, we had to deal with the usual dirty data culprits. How do we deal with NAs, nulls, and coded values? Are there errors? Are the data complete? Are we seeing what we expected? Data integration is a series of processes that transforms multiple input datasets into a single dataset for our project needs. Integrating SEDEN and SURF, databases with different purposes and sources, required us to develop a schema to accommodate information from both sets of data. This required some formatting of our original data, such as formatting date columns, transforming spatial data to be in the same coordinate system, and splitting columns with combined comma-separated information. We discovered some duplicate data represented in both datasets. So we developed methods for finding exact and partial duplicates.
And of course, this is not a linear process, so I'm going to give some examples and tools. While QA/QC procedures preceded integration, we still needed to do more QA/QC following integration. Like Skylar said, we knew there was duplication in data submitted to these databases. To remove those, 2 available functions are duplicated, which removes exact duplicates, and distinct, which removes duplicates based on specific columns. The setDiff function was essential to choose the most appropriate methods for duplicate removal by allowing comparison of records removed via one method versus another. We chose distinct because it allowed us to account for differences between the databases, essentially by assuming that samples collected in the same location on the same day measuring the same analyte via the same collection method were the same record, despite differences in other columns. By exploring the results of our QA/QC procedures and asking why differences in duplicate detection existed, we discovered that we couldn't require result to be identical because the units had actually been converted for records in SURF. And we also needed to use coordinates to require the locations to match, since station names were often recorded differently in CEDEN and SURF. Another example. SURF had a column declaring data source, which identified many records as having come from CEDEN. I used those records to test my duplicate detection method. I found many SURF records labeled as from CEDEN, which had no match in our CEDEN dataset, almost all of which had concentrations equal to 0. After locating those records in the original CEDEN dataset, I found that they had a blank in the result column, rather than a 0 as observed in SURF. Because our initial QA/QC required numerical results, those records had been omitted. That led us back to the metadata to explore further what a blank result truly meant and under what context. Fortunately, CEDEN has great metadata and detailed upload instructions. There was an additional column required to interpret blank results called result qual code. While codes ND and DNQ indicated low concentrations, only a NR code indicated that the results were not reliable and should be omitted. With this discovery, we were able to retain more records where an analyte was assessed and found to have an extremely low concentration.
Data often is used in unanticipated ways. Based on our challenges, we have some essential recommendations for researchers and data managers creating a data set. Specify the coordinate systems of spatial information within your data. Use a standard date format. Avoid combining data with commas and use separate columns instead, and avoid the use of null. If you're interested in learning more, here are some helpful resources. Thank you for joining our presentation. We'd also like to thank partners, funders, and collaborators.